Dots and lines, the origins of graph theory. In the 18th century, the city of Königsberg consists of islands where two branches of the river Prigel joined. Today the city is called Kaliningrad and in Russia, on the Baltic Sea. Seven bridges connected various islands as shown in figure 9.1. Mathematics for centuries to come was greatly enhanced by this innocent fact. In 1726, the most prolific mathematician of all times, Leonhard Euler, became interested in the following question. Is it possible to walk through town, starting and ending at the same place, so that we use each bridge exactly once? The notion of graphs. Eulerian walks. Euler understood that the shape of the islands and the river does not influence the answer to this question. He recognized that the only relevant pieces of information here are those of connectivity, that is, the number of bridges between any two islands. Therefore, instead of using the map of Königsberg, he used the simple diagram. Here the dots represent the land masses and the lines represent the bridges between them. It is clear that a walk Euler was looking for exists if and only if you can draw the diagram, so that you never lift your pencil. You go through each line exactly once and you start and end at the same point. Such a diagram made up from points and lines connecting some pairs of those points is called a graph. The dots are called the vertices of the graph and the lines are called the edges of the graph. In this book, we will only discuss graphs with a finite number of vertices and a finite number of edges. The number of edges connected to vertex A is called the degree of A. This simple model proves to be incredibly useful. The theory of graphs is a very extensive part of combinatorics, as there are plenty of problems of various nature that can be solved by this simple model. Recall that we have in fact used graphs in a surprisingly powerful way to solve the problem of example 1.7. In our walk through combinatorics, we would like to emphasize the diversity of these problems. First, however, we need to introduce some basic terminology. It is possible that in a graph, there are multiple edges joining the same pair of points, or there are edges that start and end in the same vertex. Such edges are called loops. If a graph G has no loops and has no multiple edges, then we will say that G is a simple graph. A sequence of distinct edges E1, E2, E3 until Ek is called a walk if we can take a continuous walk in our graph, first walking through the edge E1, then the edge E2, and so on. In other words, the endpoint of Ei is the starting point of Ei plus 1. Note that this happens if and only if we can draw the set of edges E1, E2, E3 until Ek so that we never lift our pencil from the paper, and we first draw E1, then E2, and so on. If in addition we start the drawing at the same vertex where we end it, then we say that E1, E2, E3 until Ek is a closed walk. If a walk uses all edges of G, then we call it an Eulerian walk. If a walk does not touch any vertex twice, then we call it a path. If we put two or more graphs next to each other, we can certainly call the union obtained this way a graph. Still, it is natural to think that this new graph is not quite as good as the original graphs. For instance, there are pairs of vertices so that you cannot get from one vertex to another through a path. This is a very important difference and motivates the following definition. Definition 9.1, if a graph G has the property that for any two vertices x and y, one can find a path from x to y, then we say that G is a connected graph. If G is not connected, then let K be the smallest integer so that G can be obtained as the union of K connected graphs. Then we say that G has K connected components. We also say that vertices U and V are in the same connected component if there is a path from U to V. In other words, the connected components are the maximal connected subgraphs of G, that is, connected subgraphs to which we cannot add any new vertex of G without forcing them to lose the connected property. Now we are in a position to state and prove Euler's theorem, theorem 9.2. A connected graph G has a closed Eulerian walk if and only if all vertices of G have even degree. Proof. First, we prove the only if part. That is, we show that if G has a closed Eulerian walk, then all vertices of G must have even degree. Indeed, when we take the closed Eulerian walk W, we visited each vertex a certain number of times. Take A. Let A be the vertex that was not where W started, and assume we visited A exactly 8 times. This means we entered A exactly 8 times, and we left A exactly 8 times. As we assume W was a walk, we had to do this using different addresses, so we used 2A addresses. On the other hand, W contains all addresses of G, so A cannot have any additional addresses. Therefore, the degree of A is 2A. This shows that the degree of any vertex other than the starting point S of W is even. Finally, note that S is not only the starting point of W, but also the end point. So, if we visited S exactly t times between the start and the end of W, then we use 1 plus 2t plus 1, which is equal to 2 times t plus 1 addresses. Therefore, the degree of S is 2 times t plus 1, and our claim is proved. Now assume all vertices of G have even degree and prove that G has a closed Eulerian walk. Take any vertex S and start walking along the edge E1 to the other point, endpoint A1 of that edge, then walk along any new edge E2 that starts in A1. Continue this way using new, previously unused edges at each step until a closed walk C1 is formed. As G is finite, such a closed walk will always be formed. The first closed walk will be formed when we first revisit a vertex already visited. We cannot get stuck at some vertex before completing a closed walk, as each vertex has even degree. So each time we enter a vertex, we can also leave it, except possibly the initial vertex. If C1 is equals to G, then we are done. If not, then choose a vertex V in C1, so that C1 does not contain all edges adjacent to V. The alert reader can ask now how do we know that there is such a vertex V? Let us assume that there is not. As C1 contains less edges than G, and supposedly C1 contains all edges adjacent to all vertices it contains, there must be a vertex A that is not in C1. However, G is a connected graph, so there must be a path connecting A to any vertex in C1. Start working on this path from A to any given vertex of C1. When you reach C1 the first time, you will reach it in a vertex V that is in C1, but not all the edges adjacent to it are in C1. Indeed, the one that has just ended in V is not. This proves, by contradiction, that such a vertex V always exists. Figure 9.3 illustrates this situation. Let us now omit all edges of C1 from G. We get a graph in which, again, all vertices have even degree. Starting at B, let us take another closed walk C2 in the remaining graph. We can then unite C1 and C2 into one closed walk in G. Indeed, if we start walking by C1, we can stop at B, walk through C2, then complete our walk by using the remaining part of C1. If the new walk C1 union C2 contains all edges of G, we are done. If not, then let us omit C1 union C2 from G and find a new closed walk C3 in the remaining graph. As G has a finite number of edges, this procedure has to stop after a finite number of steps. Therefore, after a finite number of steps, C1 union C2 union C3 and so on union CK will be a closed walk containing all edges of G. This proves that we cannot walk through all bridges of Konigsberg so that we end where we started, and use each bridge exactly once. Indeed, the graph shown has 4 vertices of odd degree. What happens if we relinquish the requirement that our walk start and end at the same place? The answer to this question is a direct consequence of theorem 9.2. Corollary 9.3, let G be a connected graph. Then G has an Eulerian walk starting at vertex S and ending at a different vertex T. If and only if S and T have odd degree and all other vertices of G have even degree. Proof. Add a new edge joining S and T and call it this new graph obtained. We call it H. Then H has a closed Eulerian walk if and only if G has an Eulerian walk from S to T, so the claim follows from theorem 9.2. We have seen that the parity of the degrees is an important property of a graph. The following theorem shows a basic fact about these parties. Theorem 9.4. In a graph G without loops, the number of vertices of odd degree is even. Proof. Take such a graph with E edges. Let D1, D2, D3 until Dn be the degrees of the n vertices of G. We claim that D1 plus D2 plus D3 and so on plus Dn is equals to 2e. Indeed, each edge contributes 1 to the degree of exactly 2 vertices, namely its 2 endpoints. So, a total of e edges will result in a total of 2e in the sum of degrees. Therefore, the sum of degrees is 2e, which is an even number. This implies that there has to be an even number of odd summons in D1 plus D2 plus D3 and so on plus Dn.